Welcome back to another AP Pre-Calc video. Today we're looking at 1.13 when we're talking about Pascal's triangle and binomial theorem. This is a weird conversation. So first, let's just talk about what is a binomial. A binomial is simply just two terms, right? X plus 3, that is a binomial. There's two terms. So binomial theorem states that, okay, if you have a binomial and you raise it to some exponent, there is this method you can use to simplify it. For example, if I had x plus 3 squared, what I could do is I could try and square that. X plus 3 times x plus 3. And you could go through your distribution to start to multiply this stuff together. Once you do that, we could always combine our like terms. X squared plus 6x plus 9 would be our final answer. Okay, but what if I had something more challenging? What if I had something now that was like x plus 3 raised to the 5th power? Well, then you'd have to have x plus 3 written 5 times, where this expression just gets longer and longer, and you're multiplying a lot more different terms together. You'd multiply these first two, and once you have that, then you would have to multiply that with the next x plus 3, and distribute, right? And that just looks exhausting. That looks like a lot of work. So instead of just writing it out and trying to multiply this all together, there's what's known as the binomial theorem. The binomial theorem is what you see in blue here. This entire thing is binomial theorem, and it looks complicated, but it's really not too bad once we start to look at an example or two to break this down. Okay, I don't want to talk about this too much. I'd rather have us process it in an example. In order to use the binomial theorem, what we're going to do is we are going to use Pascal's triangle. Pascal's triangle helps us figure out the coefficients of each term. The way you determine which row to use is the degree on your polynomial. For example, if I have x plus 2 to the 5th, I would use this 5th row as I am creating my expression. Let's look at how this works. So when you go through it, let's talk about our first term and our second term. Our first term in this case is the x. The second term in this case is the second term in this case is the 2. Well, whatever your first term is, whenever you're creating this expansion, you always start with that first term and you give it the degree of the polynomial, x to the 5th. Whatever the second term is, the degree on that one starts at 0. Okay, but we still need to use Pascal's triangle. Pascal's triangle tells us that these values are the coefficients. So this is the first term. So I'm going to use the first number in that row. I'm going to use a value of 1. Let's continue this process. Okay, we go over to the next spot. The next value in Pascal's triangle is 5. So I have plus 5. Now I need my x again, the first term, but our degree on the last one was 5. So as you write the first term, the degree always goes down by 1. So first term was x to the 5th. The second term is now x to the 4th. When we do that, the second term is just doing the opposite. Its degree, its exponent, is increasing. Now it's 2 to the 1st. We continue that process. The next value of Pascal's is 10. We multiply that with our first term with 1 less in the exponent. And you multiply that with the second term with 1 more in its exponent. And as you keep expanding this, you keep following that exact same process. Plus 10. Now I multiply it with x squared. And then I multiply that with 2 to the 3rd. Continue that process, plus 5. Go down a degree on the x, that's x to the first. And last part for your 2 there, 2 to the fourth. Finish it up with the last term. Now it's plus 1. Now my x is x to the 0, and I get 2 to the fifth. Realize the first and the last term here both have something raised to the 0 power. One thing we know is anything raised to the 0 power is always 1. So do I need to write out 2 to the first or 2 to the 0 or x to the 0 in these expressions? I can actually forget about those because all that is really happening there is that would be a value of 1. Same thing with the x to the 0 at the end. That is really just a value of 1. So I don't need either of those in this expression. Now comes the simplification. Simplify this as best as you can. I have 1 times x to the fifth. Well, that is just 1x to the fifth. The next one, I have 5 times x to the fourth times 2. Break that down best you can. 5 times 2 is 10. X to the fourth is just x to the fourth. Okay, this next one, I have 10 times 2 squared. Okay, 2 squared is 4. 4 times 10 is now 40. X to the third is x to the third. 2 cubed is 8. So 8 times 10 is 80. X squared is x squared. This next one, 2 to the fourth is 16. 16 times 5 is also 80. X to the first is just x. The last one is 1 times 2 to the fifth. 2 to the fifth is 32. So I would just add 32 at the end. That is our simplified form. Notice the degree on the x, the exponent there is decreasing by 1 each term. Let's look at another example. This one is x to the, or a polynomial raised to the fourth here. So we have a binomial to the fourth. Same process. Now let's look at the fourth row of Pascal's triangle. Pascal's triangle, we start with a 1. And then, okay, take the first term, which is 2x, and raise it to the degree of your binomial, which is 4. Then you multiply that with the second term in this case, which is negative 1 to the 0. Remember, I don't need that 1 on this term, so I can get rid of it. Okay, plus 4. That's the second term in the Pascal's triangle. Times 2x, go down 1 degree. Multiply that with the second thing, negative 1. That is going up in degree. It's going up in its exponent. Continue that process. Plus 6. Take the 2x, go down 1 exponent. The negative 1. Increase its exponent. Go to Pascal's triangle, find your next value. Decrease the exponent on your first term. Increase the exponent on your second term. Last thing, do that one more time. Plus 1. 2x to the 0. Again, it's raised to the 0. I don't need that. I can get rid of it. So now I just have negative 1 to the fourth. Let's start to simplify. 1 times 2x to the fourth. Well, x to the fourth is 4. 2 to the fourth, that's in the parentheses, so it's also getting raised to that exponent. 2 to the fourth is 8. Multiply that with 1, it's still 8. Okay, 2 to the third. 2 to the fourth is 16. That's my fault. 2 to the fourth is 16. 16 times 1 is 16. 2 to the third is 8. That was my fault. Okay, so that'd be 8. 8 times the 4 in front then is 32. X to the third is still there. But notice that is multiplying with negative 1 to the first. So what that's going to give me now is 16x to the fourth. Negative 1 to the first is still negative. So now I get negative 32x to the third. Okay, let's see this next one. 2 squared is 4. 4 times 6 is 24x to the second. Negative 1 squared is just positive 1. So, okay, I'm going to add 24x squared to that. Multiplying by 1 is not going to change it. Okay, look at the next one. 2 to the first is just 2. Multiply that with the 4. That would give me 8 there. Negative 1 to the third. Negative 1 to the third is just negative 1. So, okay, this now becomes negative 8x. Same thing with the last one. 1 times negative 1 to the fourth. Okay, well, that's 1 times positive 1, which is still 1. And now you have your final form. Let's try and go through one more example for this. Okay, Pascal's triangle, we know that the values are the same because this one is also raised to the fourth. So I'm going to fill each of those in real quick. I'm going to take my first things, 3y squared, raise that to the fourth, and maybe I'll just go ahead and fill in each of those decreasing by 1 for the rest of these terms. Sorry, excuse the bell. Okay, so continuing over, move this out of my way. 3y squared raised to the first. The last one doesn't need it. That says now let's go back for the second term. Second term is a z to the 0 on that first one. Okay, I don't need that first z. Second term I do. That's z to the first, z to the second, z to the third, and z to the fourth. Okay, now let's start to simplify. 3 to the fourth, 3 times 3 is 9, times 3 is 27, times 3 is 81. 81 times 1 is just 81. Okay, but I have y squared raised to the fourth. If a variable has more than one exponent, you multiply those exponents. So that's 81 y to the eighth. 2 times 4 for the exponent is 8 there. 3 to the third is 27. 27 times 4 is 108. Multiply your exponents. Something raised to 2 exponents, you multiply them. Y to the second and to the third gives me y to the sixth. Don't forget the z to the first there, which is just z. 3 squared is 9. 9 times 6 is 54. Y squared, multiply those, that gives me 4. I also have z squared now in that expression, in that term. 3 to the first is just 3, so 3 times 4 is 12. Y to the second and to the first, okay, I'd multiply those, that's just squared. Don't forget the z to the third, that's still following along with. And do it for the last term as well. 1 z to the fourth should just be z to the fourth. That is binomial theorem. That's how we can expand two terms raised to some power, going through that entire process with Pascal's triangle. Okay, this formula told us what the process was. The formula looks a little bit weird, but as you can see, the first term does lose an exponent each time until it goes away. Same thing with the second term. It's gone originally, but it gains an exponent each time. The values in front was simply us using Pascal's triangle for each of these weird kind of formats there. Okay, looking at those combinations. That is all for 1.13 Pascal's triangle. Thank you guys for watching.